Yeah, Andrew is lost. Okay. Shall I? Okay, so let me start. So I'm going to show to you a new construction of constant scalar curvature Keller metrics on, well, typically projective varieties, but in general for Keller manifolds. And this is joint work with Alberto Vanilla from Beijing. It's supposed to be appearing next week, hopefully, on the archive. Now, of course, I mean, just a very, very quick introduction. All behind this story is to try to have slides like this for higher dimensional manifolds. So, of course, in the case of Riemann surfaces, we know that I'm going to speak only about compact manifolds. So, for compact manifolds on the complex dimension 1, everything is clear. We have the famous dichotomy, negative, 0, and positive curvature. And the point is, and we have uniqueness of such metrics, but the point, the issue here is that, of course, in complex dimension 1, there is essentially only one notion of curvature. While when you go to higher dimensions, you have to choose which curvature you want to prescribe or to study its constancy. So, and typically what you do is by the usual staircase, Riemann, sectional, and then Ricci, leading to the famous Keller-Einstein problem, or the weakest one, which is the scalar curvature. And of course, going down this famous staircase, what you see is that, of course, the number of manifolds admitting such metrics grows. And the hope is that, of course, constant scalar curvature, as in the real case, in the famous Riemannian case by the Yamabe, the solution of the Yamabe problem, you would hope that every manifold, every Keller manifold has a constant scalar curvature Keller metric. Now, this is known to be false since at least the mid-80s, thanks to the work of Futaki. Now, Futaki came up with actually the definition that you see on violet on top. The ingredients to construct a number that he invented is the following. So you take a compact Keller manifold, the metric, the Riemann associated metric is G. You take a holomorphic vector field if it exists on, well, it always exists. You could even take 0 if you want, but a non-trivial one if you want something non-trivial. And then you integrate the action of the vector field over what is usually called the Ricci potential of the manifold. Basically, it's that function up to a constant whose Laplacian gives you the scalar curvature of your Riemannian method. Okay. Now, this looks like a completely arbitrary game. It turns out there is a simple observation is that, of course, this number, if you have a constant scalar curvature metric, then this number turns out to be 0 immediately because the function, the Ricci potential turns out to be positive, constant, and then any vector field will kill a constant, and so you are integrating 0. Okay, so the point is that, of course, you might suspect that this is 0 always by default. It turns out it's not the case. Now, at the beginning of this century, Donaldson made a critical observation. He observed, and I mean, he proved that at least in the projective case, this number actually turns out to be closely related to, I mean, you can actually compute using the asymptotic expansions. So if you are in the polarized case, the projective case, of course, you are looking at the Keller class, which comes from a line bundle, and you take the space of homomorphic section of this line bundle, and you go and see how it grows with the powers of n. And by Riemann rock, you have something like that. And you also go and see how the weight of the sister action, which is kind of a generalization of the homomorphic vector field, grows as the power of the line bundle grows. Now you take this funny combination of the coefficients and you build a number. Now, what Donaldson proved is that this number actually turns out every time you can compare them. So when the manifold is polarized, then these numbers are actually the same. And this actually proves automatically one of the most delicate properties of the Futaki invariant, which is the fact that the Futaki invariant is invariant for any metric. This is a little miracle if you look at this formula. If you take any metric in the same Keller class, you would get the same number. Now, if you look at that formula, it's absolutely mysterious. Everything depends on G. H will change, the Laplacian will change, S is changing. everything changes. Now, the point is that everything changes in a way that if you argue by dd bar phi, everything disappears. Now, in Donaldson's version of this, of the Futaki invariant, of course, this is automatic. As you can see, it is actually not even need to define a metric. These are all algebraic numbers. Now, the point, in any case, the point is that these numbers turns out to be non-zero quite often. So the moral is that we expect few manifolds to have metrics of constant scalar curvature. In some sense, this is bad news because our hope was to find a canonical metric everywhere. On the other hand, this, as usual, makes the problem interesting. So when do they exist or not? Now, as for the more famous Keller-Einstein, which I'm sure you are more used to, for the Keller-Einstein problem, you could try to see what kind of PDE this becomes. So as for when you generate the complex Monge-Ampere equation, for the Keller-Einstein problem, here what you do, you pick a random metric omega 0 and you try to deform it with d bar phi to a constant scalar curvature metric. Now, unfortunately, this I wrote it. I will not use it for the rest of the talk, but just to show it to you, it's a hopeless non-linear fourth order PDE equation. And there's absolutely no way to solve. I mean, nobody has ever found one single example by looking at this equation, by solving this equation. So, what is more useful in terms of, for example, building a good deformation theory and so on, so at least you start with something that you know and you try to reform, is to look at the linearization of this equation. So you build a family omega t, and then you take the derivative of scalar of the scalar curvature equal to 0, and you go and see what does it happen. Now, what it happens is that this kind, of course, is a fourth order operator this time. This is typical. I mean, in the case of the Keller-Einstein problem, you are just producing the Laplacian. Okay. Now, in the case of the scalar curvature problem, you are producing the V Laplacian plus the contraction between the Ricci curvature and the d bar operator. So it's kind of a mix of a fourth order and a second order equation operator. It's famous, of course, from the Riemannian point of view, so the Nervitz operator. And here there's a little miracle happening because actually looking at this expression, you can say, okay, the equation was hopeless, the linearization is almost hopeless. On the other hand, thanks to Nervitz himself, and then many people, I found a paper by Lebran and Simanka, one of the best places where to learn the story. Okay, the operator is actually mysterious, but its kernel, it has a very neat and beautiful interpretation. So an element of the kernel, which I find just a function, because I'm using the scalar d bar phi. So a function lies in the kernel if it generates, as a Hamiltonian, a holomorphic vector. So the combination, the compatibility between symplectic and complex lies in these words here. So this actually shows, I mean, you can imagine the difficulty of the problem. I mean, when at least the linearization is an invertible operator, you would expect the problem to be easier. So in some sense here, this is one and probably the most important place where you can see that the appearance of holomorphic vector fields creates problems, which is, again, from the geometric point of view, is actually strange. I mean, we tend to think of symmetries as a positive sign, a good sign. Actually, symmetries, and in particular continuous symmetries, actually are obstructions to the solutions to this problem. So, okay, in some sense, forget this. It was a good excuse to review a few things. And then people have tried to say, okay, maybe it's not the direct PDE approach, the good one to solve the problem. Maybe, again, as for the Keller-Einstein problem, a good idea is to try to implement a direct variational approach to the problem. So what does it mean? Just to find a natural functional whose critical points are the constant scalar curvature metrics, and then find some way, what is called the variational problem to prove that the functional is coercive in some sense. Now, for reasons that I don't have time to explain, but they hold also in the Keller-Einstein case, the right functional is really quite bad to see. It's what is called the Mamucci K energy, which looks like this. I wrote it again. Well, I will use some of these terms later, but the point is it's quite discouraging. If you are discouraged now, I'm still discouraged after almost 20 years, and I mean, I wonder, especially when I was younger, the point is, this is the right function. In terms of the right interpretation of the whole variational approach, this is essentially the Kempfness functional for a given action of the diffeomorphism group on this problem. So from the symplectic point of view, there is nothing to do. This is the right functional. It has a nice property, of course, that the derivative, the differential of this functional gives you automatically the constant characteristic equation. So then the question is, what does it mean for such a function to be coercive? Actually, in this literature, the word coercive has been essentially replaced by the word proper. So it means what an analyst would call coercive, meaning basically once you give me a reasonable distance function, basically what you are asking is that the functional grows more than the distance. I mean, as some function which goes to infinity, is k f of I. Now in this situation, again, it's a classical. This is actually only reported by the Claire-Einstein problem. This is the setup of so also solving the Claire-Einstein problem. In this situation is nothing. And actually, even since I will be making this comparison quite often, let me just say the constant scalar curvature problem reduces to the Claire-Einstein problem if you are looking at the anti-canonical class of a manifold. Okay, so if a constant scalar curvature metric lies in the anti-canonical class, then it's Einstein, which is kind of. So this the constant scalar curvature problem. You can think of the constant scalar curvature problem as the Einstein problem in the wrong Kerr class. Okay. Now, okay, you build this theory, and then, but then the actual reason for building this theory is to have a theorem like the functional is coercive if and only if the problem has a solution. Now, strange enough, this took almost 40 years to be proved. It's not that you build the complicated things in order for having the theorem easy. I mean, the theorem was actually hard itself. Now, in the Claire-Einstein case, this was done by Tian for the holomorphic vector fields, and then Douglas-Wu trying to cover the case of the holomorphic vector field, the presence of holomorphic vector fields. While this is quite recent, in the past 5 or 6 years, the situation has been proved, clarified because of the constant scalar curvature case. Bellman Douglas-Wu proved the arrow to the right, and then in a series of papers that will come up quite often, there is a talk by Chen. It was also proved the other application. So, okay, so you might say, at least the variational approach stands. We have a reasonable candidate as a functional. Now the question is, are we able to check that this function is proper? I mean, after all, everything was born, the problem was born, say, I give you this algebraic manifold, does it, and this Kerr class. Does it have a constant scalar curvature metric in that class or not? Now, if the answer is, okay, check that function is proper in that Kerr class, I mean, that's essentially a non-answer, okay? Well, looks like a non-answer, but I would like to show at least in some cases how to manipulate this thing, so to make it efficient, okay? In particular, okay, so this was a little, the end of the introduction. So we don't expect too many algebraic manifolds to have such metrics. We don't believe the direct PD approach should be the right one. We hope that the variational approach can do something. Now, still, it's hard to imagine that the direct variational approach gives something if you know nothing about the manifold and the Kerr class. So the idea now is start with an object where you know the answer and perform some operation. I mean, and then there is the freedom to choose. In the past, I played this game with the blow-ups of manifolds at points. Now the operation I have in mind, it's a new one. It's a different one, and it's the one of Galois covers. Okay, so what does it mean? Galois cover. Galois cover means now I take a base manifold N, and I suppose that I know something there. I know, for example, that there exists in one Keller class one constant square curvature. See? I have a Galois cover just means it's a cover whose quotient is the one below. So there is nothing mysterious about this word Galois. Of course, this translates into algebraic properties of the fields of functions and so on. This doesn't matter. It's simply n quotient G is n. So out of this situation, can we say something about the pullback? I mean, the covering space. Well, let me first give you the right and immediate call. Well, pullback metric. Of course, pulling backs preserves constant character, preserves everything, preserves Einstein. I mean, you make the covering map an isometry, so everything will work. The only problem is that the pullback of a metric under a cover is not a metric. Okay, because here I'm definitely thinking of the ramified things. I mean, of course, if everything is unramified, okay, you pull back and the problem is trivial. But if there is ramification, you can imagine, I mean, you can imagine that from the z going to z to the d, the pullback even of the Euclidean method becomes something which blows up. Okay. Now, in fact, actually, this should have appeared later if I put the later presentation, but it doesn't matter. The point is, the pullback, it is true that you could pull back something to produce the constant square curvature metric, but what you have to pull back is a conical conical constant square curvature. So if you take a cone with the right angle, that's the problem. The angle 1 minus 1 over m over d, where d is the order of the group that you are looking at, then the pullback becomes smooth.
Let me ask you a question. So your pullback, so is this the Keller?
Yes,
okay.
it does. I can tell you later why. Now, okay. So the problem is, are you able to produce a conical conical constant square curvature metric with a given angle? Okay. With the angle given by the order of the group, essentially, or some variation of that. Now, okay, that's one possible approach to the problem. I will discuss it later. Let me just tell you again, this is a generalization of something we knew from the Keller-Einstein world. So let me remind you at least the two main theorems in the Keller-Einstein world. A few years ago with Alessandro Ricci and Gianpietro Pirola, we proved one version of this theorem. At least one, we gave one sufficient condition for the answer to be yes. So starting, now we have to start with the genuine Keller-Einstein. And then if some numerology works, this numerology here, the ramification is the right multiple with the right bounds. D is the order of the group, and beta is the coefficient related to the ramification divisor and the canonical class. Then actually you can actually lift the Keller-Einstein. This was actually generalized much later by Lee and Sulm. Now in their situation, the critical assumption is that they need to assume the unfortunately here is a jumping notation. The branch locus, the one which lies below, is again a negative multiple of the canonical class, but now they need to assume that it's smooth and irreducible. It's genuine and smooth divisor, and it will be only one component. Now, again, what they prove, again, passing through the conical work, is that if this multiple is greater or equal to 1, then actually there exists a smooth Keller-Einstein metric above. Okay, so this is basically what we knew before. On one hand, I mean, this is what that was the part coming from the Keller-Einstein picture. As I mentioned, in all this story about constant square curvature metric, Cheng's produced in the past 5 or 6 years 3 pieces of work. They are all published on the Journal of AMS now. Rightly so, there have been a major breakthrough in the theory. One of the papers is actually about existence results. So I copied from their paper the main existence result, which is relevant for us, which is this corollary 1.5. Now, what they are saying is the following. So forget for a moment the second. The second is not really relevant for us. It's the first one, which is interesting. Not that for them there is no covering, there is no blow up, there is nothing. There is only one single manifold. So they ask the root question. I mean, give me a manifold, a Keller class. I want to know whether there is a constant curvature metric there, without any construction side. Then they give, under few assumptions, alpha of n is the famous log canonical threshold of the manifold and so on. Under few assumptions, numerological assumptions, and this is the main assumption here, is the condition relating the first class of the manifold, the Keller class that you are looking, and they want the positivity of this combination, linear combination. Then again, they prove the existence of the constant curvature. Now, if you take that statement in our situation, so suppose that their M is really the one which covers N, and their omega is actually the full vector of a constant curvature class. What they are really asking is the following. They are saying, they are basically, this is standard translation, so I'm not hiding anything. What they're really asking is that the canonical class plus the branch locus is NF, is numerically effective, and this combination, because this is really the C1, this is really the first class of N. Yeah, minus this is the branch class of N. So basically, just put this information there. What we're asking is the netness of these two line bounds of Keller classes. The classes correspond to these line bounds. Okay. Now, NEF, I don't know, I think NEF means it's a line bundle whose restriction to every curve it has positive degree. It's kind of a intuitively but wrong. I'm sorry, I mean, I'm recorded, so I'm not going to say something that can be used against me, but it's kind of thinking about possible limits of ample line bundles, okay? Some kind of limits of ample line bundles and okay. So this is what was known, especially applied, and as I said, Cheng's result has nothing to do with covers in particular. This is a completely general statement. But applied to this, they are asking Kn and this other combination to be NF.
Without any animal, the second condition is this linear combination of Kn and B is NF.
Without any?
That one.
Yes.
If you don't have any cone stuff.
No, this has nothing to do with conical.
Yeah,
so the question is, maybe I can repeat the question.
Let's suppose that B is trivial.
Yes.
What is like the last one, like what does it mean that the last line one is it's like N the canonical
well, I didn't check it, but I hope if this trigger should be automatic. I mean, this should be maybe the only condition. Kn.
Yeah, KNF, yes.
Yeah.
Yeah.
And then, otherwise, you're right. I mean, it's a good question. It's yeah. So let me first show you these statements that we proved, and then I will the rest of the seminar I will discuss what they really mean. Okay. Now we take our base manifold compact. We have a finite ramified curve cover, branch along the divisor. Now a notational caveat. In this literature, people like to write this BF. So, I mean, the ramification locus, of course, it's always the image of, sorry, the branch locus is always the image of the ramification locus. The ramification locus is for everybody the locus where the differential of the map has vanishes, okay, in some direction. So as a set, everything is clear. R and B are wherever. Now, there's a kind of difference in what kind of coefficients you put in these divisors in order And typically, in all this story, people like this notation there. So you put this 1 minus 1 over di in front of every component of the branch locus in such a way that this becomes true. It's just for having Hurwitz formula. This is Hurwitz formula, giving you the canonical bundle upstairs in terms of the canonical bundle downstairs. So you want the Hurwitz formula to look as elegant as possible. I mean, this is just numerology. You could actually put B to be equal to the sum of the pi, and then R would be the inverse image of this. But then this formula will have some coefficients or some nasty coefficients. Okay, so people like to have the formula in the neatest form, but pay the price of putting some strange coefficients in front of this B and in front of the R of the branch locus and the ramification. Okay, so but that's just the number. So you take the branch divisor. Now, okay, up to now I always said on the base manifold I assume that there is a constant square curvature metric. Actually, it's enough to assume something a bit weaker, like the fact that K energy is bounded from below. Of course, if it has a constant square curvature metric, it must be. And then what we ask in order to guarantee the existence of the constant square curvature metric, what we ask is they look like Chern conditions, like Kn plus B, but this is delta, and that's the critical thing. This line boundary should be F, and this line boundary should be F. Okay. So what is the difference? I mean, in Chern statement, basically this delta was equal to 1. It was really B1. Now we are allowing delta to be free to move in a range between 1 and these numbers. Now these DIs, what are these DIs? Now for every so and especially why there is an I associated. So D, before I said it's the order of the group. Now, for if your branch locus and your ramification divisor have many components, each component could have a different stabilizer above. Okay. So, okay, it is true that the group is big and so on, but each component might see a subgroup of the big group. Okay. So, for each component of the branch locus and the ramification divisor, you need to take the order of the subgroup which is relevant for that component. It's called the inertia. In this, for the expert, this is the inertia of the covering. Okay. And that's the DI. Of course, if you are thinking of the simplest situation, which I strongly suggest you do, there is only one component. Everything else, that's really the order of. Okay. Okay, this corollary is just a little bit of numerology, but it doesn't. In the cyclic case of order D, you can actually clean it up a little bit to get a neater statement, but it's the same. Mathematically speaking, it's exactly the same statement. It's just numerology applied to that. So, okay, what I'm saying is basically what this is that Chern result actually applies with a broader range of coefficients for the branch divisor to be put in the same as coefficients of the same line bundles, essentially. So of course, the obvious question is, well, okay, does it help or not? I mean, is it significant or not? Because otherwise, it's just playing games with a bit of numerology. Now, so this is partly what I already told you. This was the comparison between ours and Chern. It's just this delta naught appearing. Okay. But since I also mentioned the two results, my result and the region, and especially the soon, notice that in our results, and you will see also why, I will also tell you why, the result, in fact, here, the branch locus and the ramification, everything is allowed to have multiple components. In fact, it's more interesting when it does. And nobody is even saying that the components are smooth. I mean, the branch locus is completely arbitrary, and the ramification divisor too. So, in this sense, this strengthens a lot what we knew also in the Keller-Einstein case. There is no need for this kind of strict geometric assumptions on the ramification on the branch locus. Okay, so this was the discussion about the statements. But let me show you in practice what all this means. Okay, let's play the simplest possible game. The base manifold, I mean, what is the simplest constant scalar curvature manifold that you can think of? Of course, compact, that's the projective space. And let's take even the simplest possible covers, like, I mean, the cyclic covers are, of course, the simplest situation in this game. Or so you take a cyclic group of order D. You take the branch locus to be a multiple of the line bundle, of the hyperplane bundle. That's of course obliged by the fact that there is nothing else on the projective space. And then you do the numerology. You just go and check that our two conditions, how do they look like, and change conditions, how they look like, and so on. That's very easy because everything is a multiple of H. Of course, there's only H here. Not, in fact, this I should have mentioned. I mean, all these conditions are conditions on M. Okay, so just by looking at the base, I will be able to tell you if a cover with the right group, with the right class has. So just by looking at the projective space, I do the numerology for conditions 1 and 2. And basically what I get is that for the second condition, I just get the lower bound for which scalar classes. Notice that, of course, every scalar class in the projective space has a constant scalar curvature manager that's scaling. So that's just an empty bound. That's not complicated much. But so it's this one which is interesting and gives for us means lambda, the multiple of the hyperplane bundle has to be greater or equal to n plus 1. While in Cheng situation, they would get n plus 1 times d over d minus 1. And this actually leaves quite a lot of space for covers, even in very low dimensions. There would be many cyclic covers of P1, P2, P3, which would not be covered by Cheng theorem, and they can be covered by ours. Okay, so as you can see, I mean, maybe it was a bit scary. In fact, I mean, it is sometimes, I mean, checking these conditions maybe could be non-trivial, but it is often quite easy. Now, when we pass from cyclic to more complicated covers, I mean, again, there is an obvious staircase of complexity. So from cyclic, you pass to abelian, general abelian covers. Now, because again, this is something I should point out, it's highly non-trivial to be able to answer the question whether there is a cover. So if you give me a manifold, a projective manifold, and a group, I say, okay, is there a Galois cover of that manifold with that group? To be honest, when I started thinking about this question, I thought Riemann knew. And to my surprise, actually, it's a beautiful and very recent theory in algebraic geometry, due essentially to Catanese. Actually, I forgot to mention Manetti as a critical paper on this problem. And the abelian case has been, there's really a seminal paper by Rita Pardini, who gave equivalent conditions for the solution to be yes to this problem. Now, they are quite complicated in terms of algebraically, geometrically speaking. But let me point out something that we proved. Maybe it's not surprising for them, but which tells you, which shows, I hope to you, that the general abelian case actually does not differ too much from the cyclic case, in the sense that every abelian Galois cover is actually the composition of cyclic covers. Okay. So, of course, this does not answer the question whether the covers exist. So for that, you really have to study Pardini's work, which is a pleasure, I must say, not just because I'm recorded, but I mean, it's really a beautiful theory. I mean, but for in terms of metrics, I mean, once you know that the cover exists, in terms of metric, this is basically telling you, okay, you iterate the secret phase, and then you pull back, you pull back, you pull back, you pull back. Okay. So in some sense, this structure of the abelian case. Now, and what about the non-abelian case? Well, then the literature becomes completely random. I mean, there are hundreds of papers of people in algebraic geometry studying again the question. If I give you a manifold and this group, does there exist a Galois cover with that structure group of that manifold? And as I said, I mean, there are many, many papers, but it's really, there is no general theory. It's a kind of a for every group that somebody has done. Now, honestly, we fell in love with the construction by Catanese and Perroni for the dihedral group. Now, for the dihedral group, the story, I think it's worth advertising. It's the following. So, in fact, and actually on top of all this discussion about the existence or not, I should say, I'm discussing this point because at least the only thing I knew before was that for the cyclic case, there is no problem. So if you give me a cyclic group in the manifold, certainly there is another manifold which covers with that structure group that brings. And that's easy. I mean, you really construct the total space of the line bundle or something. And it's in the chapter 1 of Lazar's book. Okay. But then, if the group is not supposed to be cyclic and not even abelian, then, for example, what did Catanese Perroni did for the dihedral case is the following. You want to construct this cover, pick a line bundle on the manifold. Remember, now you have only the base. So your data are the base and the group, the dihedral group of order 2p, which is usually indicated by p. Okay. So you take the line bundle, and then the problem is, are there sections, holomorphic sections of the bundles p times L and 2 times L with the following condition. Notice that if I take a squared, so here it's like this is an a squared minus f to the p, they become essentially polynomials in the sense of sections of the same degree. This is 2pl, 2pl. Okay, a squared, so you can actually compare them. So the zero locus of this should be smooth. Okay, and then this is the open set where f is different from 0. The divisors corresponding to these two sections should meet transversely. And well, and actually they should meet. Okay. They should really meet and transversely. If you have this data, what they prove is that actually you have such a Galois cover. So such a manifold ML exists. And it is ramified exactly on this locus here. Now, for this particular, for the case of the data group, also there is a, remember in my combination, there was this DI appearing in the coefficients of the branch locus, so it's important to know what is DI. And you might say, well, okay, the group is order 2p, so presumably DI will be 2p. No, here the geometry is a bit, it's richly complicated, so in fact, actually this DI is equal to 2 for any I. So this is the stabilizer of every component of the ramification local is always this one can check by hand. Okay, so with this theory, for which of course I take no credit, it's all done by Catanese and Perroni, we can again do the numerology for our theory. So now at least we know, now with that data, we know that the covering exists. So we can check whether the conditions for the existence of the metric are satisfied, when they are satisfied. Okay, we played a game with many examples, but actually they all end up with the same story. So let's play the game with the Pn again as base manifold. Again, we take lambda, L, this line bundle that builds the whole theory of the covering, the lambda H for some lambda. And so now the branch locus is related, remember, as the zero locus of a section of 2PL, so that has to be 2P lambda H. With the hyperplane bundle, you plug in the objects, so Kn plus the delta, and this strange combination of things. And then you see what does it do. So the condition actually both will become equivalent, and for the case of Pn and the products delta lambda. And the moral is exactly the moral we found for the cyclic things. So there are plenty of solutions for which you could not apply chain, so you could not play. I mean, this object with delta equal to 1 will give you much fewer solutions than that, allowing delta in the range of 1, 2. There are many more. This delta allows you to move the line boundary. And we play this game also with other base manifolds. Unfortunately, the problem is in all this story, what I'm trying to concede to you is also we know very few examples of constant character, non-trivial constant characterization. So basically, the game is that give me something trivial, like Pn, and construct something non-trivial. Okay, these are programs coming out of frustration. Hundreds of people studying the general theory of constant curvature metrics, and they say, okay, give me an example, Pn. So, come on, this is a bit, okay. So these are machines to try to invade as many points of the geography of manifolds as possible. Okay. Among the few examples that we know, of course, for example, we take P2, Pn blown up at few points, because as I said before, in the past, I produced with Frank Paccard families of constant curvature metrics on this type of manifold. And then you can use them as a base now, and to produce other things as covers of them. But again, you do the numerology, we did the numerology, there will be the numerology in the paper, but the moral is always the same. You can actually get down to the final line and decide which pair classes of the cover will have a constant scalar curvature representative or not. I think I'm getting close to the end. So 15. Good. Well, I might not be using them all. So let me tell you now. Let me spend the last few minutes about the strategy of the proof, because as I said before, one strategy, which is actually the one which is clearly at the bottom of this term by soon, is to produce a conical constant scalar curvature of Einstein metric with the right cone angle on the base. And then you just say, okay, then you just pull back. Now, if you manage to do that, but pulling back, you win. Okay. The difficulty there is that, of course, prescribing the number, the angle, okay, I don't know how popular this has become. In this, the attempt of solving the Tiangao-Donaldson conjecture about the famous stability equivalence to Keller-Einstein matrix. Of course, conical metrics play a critical role. And of course, now we have good existence theorems and the formation theorems for such metrics, but not to the point of saying, okay, does there exist a conical metric of angle 2 pi divided by 3? Okay. And this is exactly the kind of question that this problem puts. So unfortunately, those theorems, I mean, they help, but they don't solve the problem. So on top of that, you could actually, but now, in fact, actually, the machinery is developed even after Chen-Donaldson solution to the big conjecture. The developments for we actually, in fact, the first version of the paper we wrote was with this machine, with the conical matrix machinery. On the other hand, if you implement it, all these theorems require, and you can imagine easily why, that the branch locus is very nice. This is exactly what Lee and Sun for the Keller-Einstein problem. The same is that you can implement this strategy in the constant scalar curvature problem, but you have bounds, clearly obvious bounds on the geometry of the branch locus. As soon as the branch locus will have two components, you don't even know exactly what it means to be conical. Okay? And if it's non-smooth, you have absolutely no idea. Okay? So, since actually part of the game was to remove this strict assumption in Lee's paper, we definitely didn't want to follow the conical approach because we knew that the branch locus would have to satisfy very strong geometric condition. Now, the winner here came by using a different space. I mean, technically speaking, it depends. When you look at the Mabuchi K energy and so on, all these functions, on which space you are looking at. Okay. So if you look at the space, this function on the space of smooth potentials, of course, it's one thing. If you allow potentials which will create conical singularities, or now it's, I think we are going to hear soon, tomorrow, soon, very soon, a lot about another type of space, I mean, a much more recent type of space of potential, which turns out to be incredibly effective in producing, which is actually the one Chen used also in their both regularity and existence approach. So this is space E1. Basically, these are functions of finite energy, but energy in the sense that I wrote here. So, a beautiful thing about this type of thing is that actually to check properness, this is something we wrote, but to check properness of the log K energy. The log K energy is the one which will actually give you the, virtually speaking, the conical method below. Okay, so, but you don't have to use the word conical because it's not really, there is no really a cone, there's not even a tangent space. Okay, so check the properness of the log K energy. Actually, it surfaces to check the properness on the space of smooth potential, which of course is typically much easier. And with that, the two critical observations are the following. If you take now that H now means smooth potentials. So first of all, the K energy behaves very well under cover. So of course you need to relate the K energy above with the log K energy below, where the log K energy is constructed with branch locus. Now I know this is getting a bit more technical, but in any case, that's the best you can dream of. And then the critical point is, and then the key point is to observe that the K energy is, if the K, remember the dream theorem I stated at the beginning. I mean, the dream theorem was here for the variational approach. The existence of the constant scalar curvature metric is equivalent to the properness. Okay. Now we need, and as I said, I mean, this arrow, which was really a huge challenge for more than 20 years, it was proved by Chen, and we need an extension to that, but honestly, it's not a difficult extension, definitely not comparable to the original theorem. In the fact that this arrow actually holds if you have a finite group and you are working G equivalent. Okay. It requires a little bit of attention, but it's definitely almost the same proof by Chen. Now, with these ingredients, the proof closes up in the sense you can actually lift the properness below to the properness above of the Mabuchi K energy. passing through this log K energy, which is now not the one, I mean, we are not interpreting it as the one giving conical. It does not have the geometric meaning of giving a conical metric as before. Because we don't even know what it means conical if the branch locus is horrible. Okay. Of course, if the branch locus was nice, that was the origin, the right interpretation. But actually, let me add you on one thing, because I'm done. So, so you can ask a question.
So just to see if I understood correctly, so if you have the properties of the K energy, like this, you're starting with glass on the base, and then this implies the properties of the lock K energy. So this is like
yes. No, but in fact, actually, you need less. You need less because the properties of the lock K energy is actually implied by the boundedness from below. Once you start adding the contribution of the branch locus helps.
This is why you just make this assumption.
Yes.
Okay, other questions,
And then this lemma, I mean, this would be like the generalization of the fact that to check the properties of the K energy, you just need to check it on this new terms.
Yes. Yeah, this is really the chain philosophy, in some sense. Always to get there.
And lemma, I guess.
Yes. No.
And Claudio, you consider manifold, not manifold singularity, variety.
So the question is whether I repeat, so if I consider non-smooth algebraic varieties to play this game.
I mean,
well,
feel such like then you might have a singularity without, you might have non-normal singularity, so there is normalization. I don't know if it's
So it doesn't exist. And the singular version of CSCP doesn't exist for the moment. Okay. Even the base.
is what
Am I wrong?
Yeah, no, I think at the moment it's completely out of reach. But I think at the moment it's out of reach even to make sense of the objects. If you start, for example, for non-normal varieties, I think we don't even know what to look for. I mean,
because you can define a cohomological class and singular manifold variety by assuming that something is on the regular part, and then either you get boundedness of forms, so you have the locally embedded and define this. And I don't know if it's possible. Make any sense.
no, in principle it does, but I think we are still quite far from having the machinery to attack this kind of problems. What we definitely should be able to do, I mean, you didn't ask, but just as a speculation, is to extend this to the non-compact case, to manifolds with given asymptotic behavior, or to domains with boundary behavior. I mean, this is certainly something certainly would be nice to understand. In fact, to be honest, as far as I know, this has not been done completely, at least I'm not aware, even in the Klein-Einstein case. And I think this would be worth spending a bit of time.
What do you mean?
Removing compactness.
No, removing compactness, no, but the singular cases.
Singular in which sense?
If you have a singular the normal singular.
Yes. No. I was saying, for example, given the audience, people might be more interested in playing these kind of games over some kind of domains of CN and then lift to something, or to play these kind of games for non-compact objects with given boundary behavior or asymptotic behavior at infinity or something like that. This, I think, the machinery is there. It might be hard, but
Any questions, comments? No, then.
thank you.
Start again, let's say, 4 minutes.